Hi everybody, I am Dr. Dharmaiah working as a professor in Computer Science and Engineering, KLU University. Okay, the next session in the session 2, so the second part is based on searching algorithms in our subject data driven artificial intelligence systems. Here we covered in the previous session uniform search algorithms with briefly and informed search algorithms and best first search. In that remaining are there what is the introduction of the A star algorithm and introduction to local search within a hill climbing algorithm. These are all I am going to deal with this session. Right, what is an A star? Two cost components are considered in A star, two components, that is called, see here, the cost of each node computed consists of the cost to reach the node from the root g of n equal to, that is called h of f of n is equal to g of n plus h of n. The function value depending on g of n and heuristic function value. F of n estimate the cost cheapest lowest solution to the n. A node with a lowest value f of n equal g of n plus h of n will be selected further reaching the solution. That is why here this g of n and h of n some other, that is called a best first search with a generalized value. This is some introductory part A star. Now come back to the algorithm. Here this algorithm starts with a start node and set its f value to f of f start. That is why we are dealing with that is called f of n equal to g of n plus h of n. There are two values then like that, while its open list is not empty. If its list is not empty, extract the node with the lowest value from the open list and call the current node. If the current node is goal node, the algorithm terminates the optimal path is reconstructing by parent pointer to the goal state, that is the first step. Otherwise, move the current to the closed list, expand its neighbors, or for each neighbor of the current calculate the g value. This is the calculation of g value is depending on the cost. If the neighbor is already open or closed, the new g value is higher and skip it, and otherwise you can update its value and so on. If neighbor is not an open or closed list and g value, and you can open the list of g value, h value and f value also, f value. If the open list becomes an empty and goal node has not been reached, then no path the start to the goal state, that is we can declare this. This is a very simple algorithm A star. And here pseudocode open create empty priority queue or g score or f score like what is an heuristic function and so on. See here the heuristic function, this will be highlight on this. There is a while loop and current node is goal node. If it is not that, to remove that, and best node and so on, we can travel. If each neighbor, how to calculate the neighbors? Neighbor is a best node, you can and select all the probable moves and calculate each and every time and heuristic functions until we get optimal solution. These are all different in-depth goal pseudocode for A star algorithm. For example, here a search algorithm mapping with a Romania, with a color and so on. I will dealing with that one is an example, so that we can get the solution. F of n equal to g of n plus h of n. Here See the A star all example. Here Arat is the one city, and each and every cities are connected in Romania, like the nodes and silver color. This description is given in the previous one, previous slide, and what are the distance, what are the node, and so on. Okay, that will be calculating. Okay, now for example, after expanding Arat to Sib, okay, here Sib, okay, see here Arat to here in the graph. Okay, we have an Arat. Okay, this is a starting point. Okay, what are the Arab adjacent nodes? Okay, this is this one, or Sibu is another one, and Jerland is another one, like that. See here, Gerand, Simbu, and Timsora, and so on. Okay, this is an Simbu. This is called then a cost. Okay, this is called a cost when we are traveling this one. Which one is the minimum on this, like that? Suppose for example from Arat, okay, when we are traveled to Sibu, okay, here again Arat, see the cost. Okay, here the integer values are always in a cost heuristic function, and along with a g of n, okay, g of n plus h of n, okay, based on that one. Now see here the expansion like this. Okay, these are all calculated each and every node, and based on that, okay, Arat to Sibu, Sibu to Arat, and so on, Romania, like this. This is an expansion. Okay, in this expansion, Arat to so on, okay, by after expanding the so on, okay, see the graph, this graph finally here, this is the best solution for this. The green color, okay, where we are seeing this is reached from Arat to Bucharest. This is our goal state. Okay, what is the final cost means shortest path, that is that's why here traveling salesperson problem we can get up with a minimum n number of solutions also. Okay, in this performance analysis, here the completeness, time complexity, space complexity, admissibility constants, and branching factor, memory heuristic functions, okay, we can evaluate with a star algorithm. Okay, here so many advantages are there by using this one. It will be find a solution 100%, and optimality it will giving a good one, and efficiency also very good, and flexibility we can travel anyone but the best solution, and memory efficiency also. Okay, then here disadvantage, it may not be suitable for these heuristic requirements, and not a solution within a different graphs, and path changing also it cannot be. Implementation of complexity, sometimes discussed algorithm is the best one by using this A star algorithms, and so on. Okay, here A star is an algorithm, admissibility and consistency we can apply in both two cases. Okay, for example, let us say it is a simple example. Okay, A is a graph A B C D E F G H. Okay, what is then a travels that cost here, this is called 3 plus 1, 4 plus 1, 5 plus 1, which is a minimal 3 plus 1 and 3 plus 2, 3 plus 3, like that. Okay, now the solution is okay 1 plus 1, 0 plus 3, and so on. Okay, like here f of n equals g of n plus h of n. If g equals 0, then f of n equal to h of n. See the solution. If g equal to 0, that means goal will be chosen and it becomes a GFS. If g equal to 1, h of n equal to, it will be also fewest number of steps in this case. If h equal to 0, f of n equal to g of n. See here all the possible condition. If h equal to 0 and g equal to 0, there is search will be remains random. Okay, like that. If you are unable to find all this case, suppose here the step by step algorithms we can connect with them. Okay, what are the applications we are used? Okay, here this A star algorithm used in different applications like robotics and automation vehicles, GPS navigation systems, video gaming, network routing, logistic and supply chain management, and robotic motions planning, and air traffic management, natural language processing, puzzle solving, AP path solution manufacturing, and these are all different application of A star algorithm. Okay, how to implement this one is, okay, here we can navigate with by using 2D steps and so on, and here so many variants are there, okay, but we are not covering that one. And local search introduction only. Here what do you mean local search? A search algorithm that you are defined within a designing explore search space systematically, and this systematically approach within a memory and recollecting that one, and its a goal is found, that is called a solution of that one. Okay, like this is an 8 queens problem is in a local search. Not only that, in the based on a job and so on. Okay, here the local search is used. Under this we are going to for used in a minimum or maximum solution. Okay, in this local search we are going to discuss in this chapter in this session only in our syllabus we have that is called hill climbing, only hill climbing, not steepest hill climbing, and simulated tunneling and beam search and local search genetic algorithms, these are all not there in our syllabus. Okay, now hill climbing. Okay, how we can generate with an hill climbing? Hill climbing is a simple local optimization techniques, and it is used for assuming a maximum goal, maximization of a goal. Okay, suppose for example let us say simple hill climbing and steepest hill climbing. Okay, we will deal with the following algorithm. Now look at the algorithm. Here the algorithm initiate, evaluate the initial state. First we can find out the initial state where we can start, and if it is in a goal state where it is we can out, okay, that is called quitting. Otherwise we can continue initial state to current state and so on. Loop until the solution found and new states left and apply. The following steps will be applied. Okay, what are the following steps? Select a state that has not yet been used in a current state and so on. Evaluate the new state. If it is in a goal state, then return to its kick. If it is not in a goal state, if it is returned to better than the current state and so on. If it is not in better than current state, continue within a loop and so on. Okay, this will be used. Okay, here in climbing steps, initialization condition, that is when you find the goal state. Okay, that is when you find the goal state, and evaluation order. Okay, select the neighbors and evaluation neighbors, move to the first better neighbors, and termination conditions. Okay, lastly termination conditions are used within a better performance way. Okay, this is dealing with an algorithm. Okay, detailed algorithm with a step by step we can generate it. Starting with an initial solution and current state and current value. Repeat the following steps until the termination condition. Generate the neighbors. If neighbor is generated new current state and so on, it is update. Evaluate the neighbors within a next step. Evaluate the neighbor within neighbors within a best solution. That is called hill climbing. Okay, and move the best neighbor, and whether it is reachable to the condition and so on. This will be repeating, and terminate the condition if we reach the final state, and return the solution to the goal state and so on. This algorithm is worked out. For example, let us say here there is a function f of x equal to x power 2, and such space is it is limiting between minus 10 to and plus is less than or equal to x is lies in between less than or equal to minus 10 to x or past to 10 and so on. How we can use this condition? Suppose here initial condition, if x is an f5 for example, what is an f of x? X power 2, no, 25. If x equal to 2 or x equal to 5, x equal to 10, you can produce that one. Okay, what are the nearest values? If x equal to 4, what is an x value? F of x. What is x equal to 6? What is an f of x value? So that see here the 16 and 36 and so on we can apply, that means the condition, so that we can get back the solution easily. Which one is we are picking in this case? Okay, here the performance analysis of for hill climbing, coverage the local optima, sensitivity of the initial solution, search space is an explorer. Okay, these are all different optimal solution. Optima is a very good one, okay, based on that one, and scalability, premature coverage, convergences, escape from the local optima, computational efficiency, and these are all different performance. And now this one are advantages of hill climbing. Hill climbing is a very simple, and it gives an accurate results, and efficiency also good. It is used on local search, it used based on the single object function, and it is a very greedy approach, so that we can always best select the neighbors like that, and low computational cost, so that it will be taking less time. And but in this case actually it is also having a disadvantages, the following: local optima finding is difficult for us, and lack of backtracking and premature coverages, limited exploration, escape local optima, and plateau. These are all disadvantages of hill climbing. Okay, these are all real type application when we are using this one. Traveling salesperson problem, this is getting a good solution. Not only that, image registration, network routing, resource allocations, job scheduling, robot path planning, parameter optimization, VLSI circuits placement, these are all different type of real type applications we can use this hill climbing algorithm. Okay, now lastly I am giving a small best solution which is an understable. This is an initial solution, initial state, this is a goal state. How we can reach this by using this hill climbing. Initially A, B, B, C, C here, B, C, D, A, but I want A, B, C, D like this, the towers. How it is worked out? See here, initially H value is 6 or H2 value is minus 3, H3 value is minus 1, H value is minus 4 and so on. Here A will be come down this, that is why here these two. Again B will be the D will be come down, that is why A and D. Again okay, C will be come down like that is why B, D, A, D, C. And after this what is then our goal state? A will be comes now, under that A again B, that is why A this will be here, that is the next step. What is the next step? Again C, okay, C will be here, that is why C will be here, and then next D will be upon this. This is a final state. See here, this is an initial state, this is a final state. Simple, we can get back with a simple one. Okay, in this one we are using this summary and the following techniques we can use. Thank you once again.